Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 26, 2025, just about a week ago. It introduces a unified framework that allows researchers to optimize training settings on a small 50 million parameter model and successfully transfer them to a 7 billion parameter model, achieving a 1.32 times speedup in training. The paper is titled, Completed Hyperparameter Transfer Across Modules, Width, Depth, Batch, and Duration. And as we'll see later, the implications for making large-scale training more efficient are really promising. Figure 1 illustrates this strategy, comparing standard global optimization against the author's granular per-module approach. On the left, the team performs a hyperparameter search on a small 50 million parameter proxy model. The middle panel shows the result of this small-scale training, where the per-module configuration, in blue, reaches the target loss over 2.3 times faster than the global baseline in red. Finally, the right panel demonstrates the key contribution, transferring these settings to a 7.2 billion parameter model. Even with a 600-fold increase in compute budget, the method maintains a 1.32 times speedup without any retuning. So, Figure 2 verifies that this transfer works reliably across both model width and depth. The charts plot final loss against learning rate with red lines for small models and blue for large ones. In the left panel, the optimal learning rates align vertically, showing stability as width scales from 128 to over 2000. The middle and right panels demonstrate the same alignment for depth, regardless of whether the residual scaling parameter alpha is 1/2 or 1. This visual proof confirms that the hyperparameter sweet spot found on a small proxy model applies directly to the large target model. Table 1 breaks down the mathematical recipe behind these results. It contrasts the standard μp parameterization in the middle column with the proposed complete DP framework on the right. While the standard approach primarily focuses on width scaling, denoted as MN, the new rules integrate depth, batch size, and total token count. For instance, the learning rate and weight decay rows on the far right now include square root factors. These specific terms allow the training dynamics to remain stable even as the duration and batch size change significantly between the proxy and target models. Moving to Figure 3, we see the impact of these rules specifically on batch size scaling. The goal is for the optimal learning rate to remain stable even as the batch size changes. In the left plot, using the proposed square root adjustment, the loss curves for varying batch sizes align vertically, sharing the exact same minimum. By contrast, the right plot shows the failure without this rule. The optimal learning rates scatter horizontally, meaning a setting that works for a small batch would fail completely for a larger one. Just as the previous figure addressed batch size, Figure 5 tackles transfer across training duration. The left panel reveals the challenge. As the token count grows from roughly 1 billion to 32 billion, the optimal learning rate, marked by the black crosses, shifts significantly. In contrast, the right panel applies the paper's square root scaling rule. Here, the curves for all durations align vertically, confirming that a learning rate tuned on a short run correctly predicts the optimal setting for a much longer training job. So, while Figure 5 confirmed the parameter alignment, Figure 6 demonstrates the resulting performance gains. These charts show scaling laws for 3 model sizes, plotting the final loss as the number of training tokens increases. The blue curves use the baseline method, which scales only width and depth, while the red curves apply the full complete DP framework with SDE scaling. In the top panel, the difference is subtle, but look at the bottom panel for the 743 million parameter model. Here, the red curve is distinctly lower, and the equations on the left confirm a better scaling coefficient, proving that the method yields superior asymptotic performance. Alright, moving beyond training curves, Figure 9 validates the final model quality on downstream tasks. This chart compares the 7.2 billion parameter models on standard benchmarks like Pika, HelloSwag, and MMLU. The red bars represent the baseline using global optimal settings, while the blue bars show the performance with the transferred per module hyperparameters. Across the board, the blue bars consistently edge out the red ones, proving that the efficiency gains from per module tuning actually arrive with improved reasoning capabilities, rather than any trade-off in quality. Wrapping up, 2 takeaways stand out. First, the complete DP framework successfully unifies scaling across batch size, duration, width, and depth. Second, this proves that expensive, per-module tuning on tiny proxy models can reliably transfer to massive runs, unlocking free speedups at scale. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.